Most of you will recognize the footage you have just seen as that taken during the disastrous incident at Ben Wa. During that incident, explosions propagated from aircraft to aircraft and to various facilities, including the fuel storage area. A number of lives were lost. A major section of the base was damaged. You cannot completely prevent explosives accidents in operational environments. But there is much that you can do to minimize damage if an explosion does occur. In this briefing, we will illustrate some means of reducing the possible damage from accidents, provide information about what to expect in the way of damage under certain conditions, and finally, give you substantiating test data obtained by blowing up actual aircraft in realistic, full-scale tests. Before proceeding, there are some basic terms we should define for you. First is simultaneous detonation, in which two stacks of explosives are close enough together that explosion of either stack would detonate the other stack so quickly that there would in effect be a single explosion with a blast pressure wave equal to that from a single stack containing the same total weight of explosives. A propagating explosion is different. This involves non-simultaneous communication from one stack to another. The bomb stacks are far enough apart so that there are two separate explosions with two pressure waves and a discernible drop in pressure between the explosions. The time between explosions can vary from about 50 milliseconds to an hour or more. Such consecutive explosions create no more overpressure at any given time than one explosion would, with respect to objects at a distance. The distance that fragments and debris would travel would be essentially the same as with a single explosion. The advantages to be gained from separating explosives into smaller stacks are obvious. The radius of damage and distance required to inhabited buildings and so forth will be much smaller. The term explosives quantity distance refers to the relationship between the quantity and type of explosives involved and the distance necessary to provide an acceptable degree of protection. The quantity distance criteria for mass detonating explosives follows a cube root scaling law which provides a constant factor called the K factor for each protection distance covered in the standard tables. This factor times the cube root of the net weight of explosives in pounds equals the required distance in feet that a given quantity should be separated from various exposures to provide an acceptable degree of protection under the circumstances. The factor varies with the circumstances, and of course there are tables covering quantity distances. First, magazine distance, which prevents simultaneous detonation. Intraline distance minimizes the possibility of propagating explosions, but personnel are seriously exposed. Public highway and inhabited building distances. At these distances, personnel are reasonably safe, except from chance falling fragments and debris and flying broken glass. All distances are based on different K factors for the same amount of explosives. The smaller the K factor, the less separation. Likewise, any conclusion or K factor for aircraft will apply to any weight of explosives load on any aircraft. Originally, these damage-limiting quantity distance standards were designed to be used in explosive storage areas. In applying such principles to a flight line environment, we must consider the aircraft and all of its fuel to reach a quantity distance solution that will give us a measure of protection throughout the flight line from propagating explosions. Bringing explosives-loaded aircraft into the picture increases the vulnerability of such aircraft to explosives propagation because of their own characteristics. 1 or 2 psi overpressure will cause minor damage on an airframe. 2 to 3 psi overpressure causes major damage, likely not repairable. At higher psi's, you can expect total destruction of aircraft. The detonation of a small amount of explosives, say 5,000 pounds max load on a fighter, would result in at least 27 psi overpressure at 102 feet. So even without considering fragments, you stand to lose the use of aircraft from overpressure alone at considerable distances, out to around 2.5 psi. Now, high-speed, low-angle fragments are a common cause of propagating explosions. We should do everything we can to reduce them. A high-speed fragment from one bomb can set off another bomb very easily. With several exploding bombs on one aircraft producing a large number of fragments, the susceptibility of other bombs loaded on adjacent aircraft would be very high. Propagation, near simultaneous, if not truly simultaneous, can be expected on nearby aircraft unless we can get rid of these fragments. We can do this reasonably well with barricades, which will eliminate most of the low-angle fragments. We'll have to accept the risk from the low-speed, high-angle fragments that go over the barricades. Parked aircraft can only be completely protected by substantial overhead cover capable of withstanding the overpressure. We therefore recommended that a realistic full-scale test be conducted. The test was given the designation Big Mama. Its purpose was to determine the minimum separation required between barricaded aircraft to provide a reasonable probability of avoiding propagation of an explosion down a line of aircraft. In the B-52 revetment, the walls were 7 3/4 feet thick and 16 feet high. You see here the positioning of the aircraft and the bins. All aircraft were fully fueled with guns loaded for the test. The donor aircraft, the aircraft to be first detonated, is in the center. The primary acceptor is A3 in the bin to the right. They are both B-52s. All others are B-47s, which represent B-52s, A1, A2, A4, and A5. The B-52s were loaded with their maximum high-density loads of 66 750-pound M117 bombs containing 387 pounds of explosives each, for a total net weight of a little over 25,000 pounds. This is the maximum explosive load for the B-52 at this time. The B-47s were not loaded with bombs, but were fully fueled and otherwise operationally configured. It has been abundantly proven that explosion of the bomb load can be expected if the aircraft catches fire. So we did not wish to jeopardize test results, fragmentation patterns, and so forth by further live loadings. The B-52 at the right, Acceptor A3, is located at our recommended K-18 distance of 560 feet. The B-47 at the far left, A1, is at a greater distance, K-24, barricaded public highway distance from the donor. A2, just to the left of the donor, represents the aircraft in an adjacent bin and is located at K6, barricaded magazine distance from the donor. The wall between the donor and A2 was reinforced with a number of H-section piles driven into the ground. A4 and A5, forward of the donor, represent aircraft across the taxiway. A4 is located at a magazine distance, unbarricaded, or K11, which would represent the separation between parked explosives-loaded aircraft normally used throughout the Air Force to prevent simultaneous detonation. Now, A5 is located at the same distance from the donor as A3, that is 560 feet, or K18, explosives to explosives from one wing rack to the next, except A5 has no barricade. The test setup has the unique characteristic of representing 3 aircraft in bins without exposing that many aircraft. In the Big Mama test itself, the aircraft landed on a desert strip at Alkali Flats. A compacted taxiway connected the landing strip with the test site. Here, the B-52 Acceptor aircraft A3 is being moved into position. This is the same B-52 Acceptor with pylons and bombs in position. The aircraft is of such old vintage that it had no facilities for the installation of wing racks. The bombs were placed in their proper position using stands. The B-52 Acceptor is in position with bombs loaded and fuses installed in their normal combat configuration. You can see the internal bomb bay with some of the bombs loaded. Here is the test site with all aircraft in position. This view was taken with a normal speed, 24 frames per second camera, 2.5 miles from ground zero. This aerial view shows the aircraft on the left beginning to burn. Here's the explosion again from ground level relatively close to the blast. It's taken with a high-speed camera at 1,500 frames per second. Note the rising dust in the foreground. This is the blast wave advancing across the desert floor. This scene, taken at 4,000 frames per second, shows the back wall of the donor revetment. You can see the shock wave going over and under the revetment wall. Now let's take a look at what happened to each of the aircraft. You will recall that A2 was to the immediate left of the donor. This scene, taken at 1,500 frames per second from the back of the donor, you see the disintegration of the aircraft as the shock wave hits it. The aircraft was 200 feet, explosives to explosives, from the donor, 240 feet center line to center line. Now let's see what happened to A4, the aircraft forward of the donor at unbarricaded magazine distance. You can see the shock wave rippling across the skiff and the tremendous amount of debris in the air. Flashes you see are high-speed fragments striking the aircraft. A4 was positioned 340 feet, explosives to explosives, in front of the donor aircraft with no intervening barricades. Acceptor A5, located at 560 feet, explosives to explosives from the donor, unprotected by barricade walls, was destroyed in the same manner as A4. However, it did not burn as completely. The B-52 aircraft, A3, you will recall, was located behind the barricade, 560 feet, K-18, explosives to explosives from the donor aircraft. Note the shock wave as it tops the revetment wall. It moves slowly across to the aircraft, breaking off the top 10 feet of the vertical stabilizer. A1 was located 745 feet, explosives to explosives, from the donor aircraft. Ground cameras revealed no significant damage to A1 from blast wave reaction during the explosion. The donor aircraft and the two unreinforced bin walls were completely destroyed. The bin wall on the left survived with some damage. This is attributable to its reinforcement with H-section piles and concrete footings. This wall, however, did not protect the aircraft A2 adjacent to the donor. The two burning aircraft forward of the donor, acceptors A4 and A5, were unprotected by barricades. The B-52 acceptor A3 was largely unharmed. This small black spot on the ground at the center of the bin wall is an engine from the donor. The other three engines are here, here, and here. The same engine distribution pattern repeated itself on the other side of the donor. The surviving B-47 is at the top of the picture here. A B-47 behind the bin wall at 745 feet, explosives to explosives, was damaged to some extent by fragments, but not nearly as much as the B-52 acceptor. There had apparently been some high-flying embers, floating pieces of aircraft, burning or at least very hot, which could have started a fire even at this distance. The spot on the wing shows that a fire did get a little start, but burned out quickly. Now, this is typical of fragment damage. The B-52 Acceptor was not repairable, but the B-47 could easily be repaired. Now let's take a look at what happened to A-5. These parts are the largest surviving from destroyed aircraft. This shows a B-52 engine just outside the reinforced donor wall that remains standing. This is an end view of the same wall showing two of the H-section piles used to reinforce the wall. Just to the right of the wall, you can see the remains of the donor tail assembly. This is looking inside the donor revetment, showing the other walls blown over. This is the outside of the wall protecting A-3, the surviving B-52. This engine came from the donor, dented this wall. Otherwise, the wall was undamaged. Here is the surviving B-52 A-3 with the donor engine in the foreground. The bombs were not damaged in any way. Fragment and blast damage was considerable. As you saw previously, overpressure broke off the top part of the vertical stabilizer. The bomb bay door next to the blast was blown in, and the fuselage showed unusual skin wrinkles. Glass was shattered, and the fuselage shows some twisting. There was no fire, but the extensive damage suffered by the aircraft due to overpressure would take it out of your inventory. This is a close-up of the donor tail assembly, all that is left of a bomb-loaded B-52. To sum up, all aircraft were destroyed except those positioned at our recommended distance or greater. Several conclusions were reached from an explosive safety standpoint. First, the spacing K-18 between the donor and A-3 will provide a reasonable degree of protection against propagation of the explosion when barricaded, as in the Big Mama test. Any significant reduction in spacing would seriously jeopardize this degree of protection. Second, the bin walls provide the amount of protection predicted. They do stop most of the high-speed, low-angle fragments. The bin walls retain these fragments regardless of whether they stand or fall, because the fragments get there before the blast wave blows the walls down. We have approved use of a 5-foot thick wall for aircraft with explosives loads of 5,000 pounds or less. A 7 3/4 foot thick wall is required for loads up to 30,000 pounds. Third, the low velocity, high angle fragments from the bombs and aircraft debris constitute a hazard that could start fires from one group of 3 aircraft to another. Group sightings of 2 or more aircraft in attached multiple bins should continue to be an operational decision based on the necessities of individual solutions and assessment of the known risks involved. In other words, how many aircraft are you willing to lose in a single accidental explosion to satisfy a certain operational commitment or fit yourself into a given land area? The next step in such protection would, of course, be a hardened aircraft shelter. We realize that conditions at many bases do not permit an optimum solution to the problem of protecting explosives-loaded aircraft. It is our hope that the information and conclusions of this briefing will be of assistance to decision-makers faced with such situations, and to all others having a need to know what to expect in explosive-loaded aircraft environments.